you know, the ones to remember, I think, are this one, and this one. If you have that, you'll have everything you need for these types of problems. So for these problems, just think back to how you could find the area under a curve using a Riemann sum, using the areas of all these rectangles and summing them up, and you'd have the area under the curve. We're going to do a similar thing to find the mass moment of inertia for this solid right here. We'll take one of these slices. They're infinitely thin, they have a length y, and that makes it convenient for us to assume that we can use a formula that we already know. It's just a generic formula sheet here. The mass moment of inertia for a rod about its end perfectly describes this scenario. You got a rod right here, negligible radius, and we're finding the mass moment of inertia about the x-axis at the end of the rod. So, using that formula, now we ask the question, what's the mass of the rod? Well, mass, we know it's density times volume, right? So we'll call density rho. And the volume, think here it's actually a rectangular prism. And it'll have a thickness we'll call t. It'll have a height, which is y, and the width we're calling dx. And that's the mass of the slice. So we have everything we need to calculate the mass moment of inertia about the x-axis of the slice. dixx, we'll call that. It'll be this formula, and real simple, just plugging things in. Y. And plugging in dm. And we have y and y squared, that'll just come in to be y cubed, and we'll actually substitute in the function that we already have, y equals square root x over k. Just plugging in cubed t dx. And by summing up all of these for all the rectangles, that's just an integral. So the mass moment of inertia of the solid is the integration of dixx. And the bounds are across the appropriate bounds. From here, in this case, it'd be from 0 to b, you know? So we'll do a similar thing for the mass moment of inertia about the y-axis. This one's a little different. We'll be thinking parallel axis theorem, right? Parallel axis theorem, this would be the value evaluated at the centroid, and it's just a rod, so we know the centroid's right there in the center. And we can intuitively say that this goes to 0. Why is that? Well, this slice is, infinitely thin. So if there's no width, then there's no mass. So mass moment of inertia is the resistance of an object to rotate about an axis. So if there's no mass to resist, then there can't be any value here, so we just call that 0. And that just leaves us with md squared. And m is the same thing, it's the same rod, so it's the same mass. So let's find dIyy. The mass, plug in 0 times d squared. What is d? It's the distance between the axes, and that distance in this case is real nice because it's just x, so x squared. And same thing, it's real easy, you plug in plug in for y again. And so you'll still be integrating in terms of y. And that's pretty cool, right? X squared dx. And the mass moment of inertia for the entire solid is just the sum of all the rectangles. So that's how I like to think about it. This is a pretty simple case that comes up a lot, so, you know, the ones to remember, I think, are this one, yes, this one, and this one. If you have that, you'll have everything you need for these types of problems. One more thing I almost forgot. A lot of problems will give you a number for the mass, but not the thickness of the solid. Because they clearly have thickness, and that you need that to find volume, and volume is one of the steps in here. So how do you do that? Well, let's say mass is like 6.7 kilograms, right? You'll be integrating it, and you won't be able to take out the terms, and you'll have blah 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 times rho times t, right? From here, it's just the old multiply by 1 trick. So you take the mass, you have 6.7 over mass. What's another way of writing mass? Integral of dm. And the integral of dm, so let's rewrite this. You have something times rho times t times 6.7 over something else times rho times t, and those just cancel, and then you'll have something, you have some numerical value. So that's how you do that.